Energy, in every shape and form, around the Earth and throughout the universe. Energy is provided by nature, even if some of it, in a deadly game of follow the leader, is unleashed by man. Energy, and more energy. No matter how, or how often it's used, regular or unleaded, energy is always conserved. But if that's a fact, and the law of the conservation of energy says it is, why isn't there always enough energy at hand? Motion itself is a form of energy, because energy takes that form when anything moves. But if energy is always conserved, how do moving objects ever get started? And once running, whatever direction they're moving in, if energy is always conserved, how can they ever stop? Some people work with more and more weight. Others try to work off some of the weight they walked in with. Yet even here, the vital question is, if energy is always conserved, why do muscles get tired? And why do weights fall? The answer, like exercise in general, has to do with work. In fact, part of the answer is work. And in exercising the conservation of energy, work has a precise definition. The greater the weight, the more strength required to lift it, of course. And the greater the height, the more work. Work equals force times height. When the work is being done near the surface of the Earth, the force in this equation is the constant force of gravity, which equals mass times the acceleration of gravity. So, work equals mass times g times height. Sometimes, force makes mass accelerate, but here, force is used to overcome gravity, to lift the weight to a certain height. In the conservation of energy, the role of work is to transfer energy from one place to another. From muscle into steel, for example. The barbell has energy because of its height. That's potential energy, which is given the symbol U. In a constant gravity field, the potential energy of any object is written as mgh. In other words, its potential energy is exactly equal to the work that was put into it. It's called potential energy because, at any given height, it's ready to go into action. The greater the height, the more potential energy stored in the weight. Potential energy that can change into motion. For all its ups and downs, potential energy depends only on vertical distance. But there must be an easier way to make the point. These machines, the mechanical ones, combine pulleys, cams, levers, and inclined planes that Galileo might have admired. A lot of expensive technology is at play here to increase or decrease, or just change the direction of the force needed to lift a weight. but no matter in what direction the force is applied. Potential energy relates only to height. And the potential energy keeps changing. Every time anything moves up or down, potential energy by itself isn't conserved. In the law of the conservation of energy, then, what is actually conserved? Toward the end of the 16th century, Galileo Galilei asked himself a similar question. But it was one question for which even Galileo failed to find an answer. Nonetheless, while using inclined planes to slow down the acceleration of falling bodies, he did find something rather fascinating. No matter what path it followed, the ball would return to its original height, almost as if the ball remembered its original position. Of course, Galileo knew that an inanimate object couldn't remember where it had been. But he realized the ball retained something very powerful. If not memory, he wondered, what did the ball conserve? The answer didn't come speedily, but speed is the key to the answer. Starting from the same height, no matter what the slope of the incline, when the ball gets to the bottom, it's always going at the same speed. The energy of the ball's original height is still rolling along, transformed into speed.